So having derived the standard normal distribution and having derived the chi-square distribution, we're finally ready to derive the t-distribution, which is of course going to power the t-test. So let's start by looking at why we need the t-distribution. So let's return to our example of students who have taken an exam with a mean of 100 and a standard deviation equal to 12. As we'll remember, we want to know how many, if we have a sample size of 10, if we were taking the mean of 10 students taking the exam, right? So I'm taking the mean of 10 students taking the exam. And I want to know how many standard deviation units that's going to be away from the mean of 100 when the null hypothesis is true. What I have to do for my z-test is I have to look at the difference between the mean of the students who have taken the exam minus the mean, right? So xi minus the mean, where this is the expected mean of all the students, and this is the mean of the 10 students who have taken the exam. And I have to divide that by the standard error, where the standard error is the standard deviation, but corrected for the sample size, because as more and more students take the exam, the mean will get closer to 100. So if an infinite number of students take the exam, the mean will be exactly 100. And then we have, just to make this a two-sided test, we multiply by 2, and we ask how many standard deviation units are we away from the mean, and that gives us our p-value. So that's all review from your first semester stats class, and also review of the standard error sublecture, which was just a sublecture or two ago. So all that works fine. But that's assuming that we know somehow that the standard deviation is 12 ahead of time. And in biology, we pretty much never know the standard deviation. So if you're looking at the weight of mice under one drug treatment, you never know the mean and the standard deviation ahead of time. You have to estimate them from the data. And so, and we can see that our test will break horrifically if we estimate this value of 12 from the data rather than just knowing it ahead of time. So all we have to do to break the test is replace this 12 with the standard deviation of my vector. So now instead of knowing that the standard deviation is 12 ahead of time, so obviously I know it's 12 for generating the data, but if we're modeling more of a real biology experiment where I don't know the standard deviation ahead of time, so all that I have to do is take this standard deviation and estimate it instead of having it from the data, and the test breaks, and it breaks in the way that I don't want it to break, which is anti-conservative. So the p-values are too small. Okay. So now of course we're going to correct this with the t-distribution. So the t-distribution, so we need to use the t-distribution instead of the normal distribution. And the t-distribution is defined as in the numerator is a standard normal distribution with an expected value of a mean of 0 and a variance of 1. And the denominator is the sort of curious set of symbols, or curious distribution. What's in the denominator is the square root of the chi-square distribution with v degrees of freedom divided by v. And v is going to be the number of degrees of freedom that you have in your t-test, and we'll talk about how to calculate that when we get to the t-test that's coming up in the next lecture. And of course the assumptions are that z and v are independent of each other, so these are just normal independent draws from the normal distribution or from the chi-square distribution. They're not linked in any way. So we can prove to ourselves that we understand dt just by it's defined in this way, right? So here's my homemade t function. The top part is just r norm 1, right? It's just a standard normal distribution. The bottom part is the chi-square distribution divided by the number of degrees of freedom. So when you do a t-test, you have to specify the number of degrees of freedom. I could have used d chi-square for that, but instead I'll just go ahead and pull r norm 1 and sum up the degrees of freedom, sum up the chi-square manually, right? So now I have the top part, which is just this standard normal distribution, and the bottom part, which is a chi-squared sum divided by the number of degrees of freedom. Do that a bunch of times and compare my homemade distribution to dt, and of course they're exactly the same thing, right? And so, and now I don't actually have this in the slides for some reason. Maybe it's too obvious at this point. But if we go to R and we type question mark t dt, this is the t distribution. This is the dt, pt, qt, and rt. So all of our prefixes that have been there all along for every single distribution in R. One last time, the probability density function, the cumulative probability density function, the inverse cumulative probability density function, and random sampling. So all of that is there for the t-distribution as well, with its one parameter, which are the degrees of freedom. All right, so the t-test has this one parameter, the degrees of freedom. As that approaches infinity, this denominator approaches 1, and the t-distribution approaches the z-distribution. So at large sample sizes, the t-distribution, the limit of the t-distribution at large sample sizes is the standard normal distribution. And we can see that with just a couple of lines of code here, where I am plotting out the this denominator here. So I'm just getting the square sum of the denominator at different degrees of freedom, right? Divided by I, right? So this part here is just this in this code is just the denominator that's here, right? And as I gets bigger, this number approaches 1, right? And so as the degrees of freedom approaches infinity, the t-distribution approaches the uniform distribution. And if we go back to the chi-square distribution, right? So what we were arguing with, this is the chi-square distribution here, this bottom part, right? So what we saw when we looked at the chi-square distribution before, right, is because the chi-square distribution as a variance term, as a sum of squares like a variance term, when the degrees of freedom in the chi-square, which is v here, or k in this plot of the chi-square distribution, right? When k is small, when the degrees of freedom is small in the chi-square distribution, you have more of the probability density function at these smaller values, because the probability density function can never be below 0, right? So at small degrees of freedom, we have more of the probability density function shifted to the left on the x-axis, so this number is larger, right? And that causes the correction for the of the t-distribution. But at when k is larger, when the degrees of freedom go large, the larger they get, the closer this approaches to 1, and the more the t-distribution just acts like the standard normal distribution. So at 5 degrees of freedom, if you plot this out, there's a big difference between the t-distribution and the normal distribution. dt is wider than d norm. That means this is going to be more conservative, right? So if you're comparing dt versus d norm, right, this extra area here. So when we do inference, we're adding up the area. Like, so if we're 2 standard deviation units away from the mean, we're adding up the area, like everything from here out to negative infinity. So because dt is wider with 5 degrees of freedom than d norm, you're going to get more probability counted up here. So the t-test is going to be more conservative than the z test. And you can see it this way on the histograms, or you can see it the same thing using the cumulative distribution function using p norm and pt instead of d norm and pt. And likewise, if you repeat the same graph at comparing 5 degrees of freedom to 1,000 degrees of freedom, the normal distribution and the t-distribution have converged, right? So at small sample sizes, the t-distribution is going to be more conservative than the normal distribution. You have extra area here that's going to increase your p-values. At large sample sizes, doesn't make a difference. The t-distribution basically becomes the normal distribution, and at an infinitely large sample size, the t-distribution is exactly the normal distribution. So let's go back to our broken statistic here. So we, again, as we've done a couple of times over these mini lectures, we've left our code in a bad place where the p-values were too small because we were using the z-test here. We were using the normal distribution. So to fix this, all that we need to do is now use the t-test, right? So I'm now estimating, this is broken because I'm estimating the standard deviation from the data instead of knowing it ahead of time. This doesn't work if I use the normal distribution. If I use the t-distribution, it magically starts to work. So that's really great, and all is well. So to try and develop some intuitions about why this works, let's go through a little bit of math. This is a little bit involved, but is sort of interesting. So let's just define x average, right? So x average is just our normal mean and our normal variance. So our mean and variance of some distribution that we're looking at, just as defined as we've been defining them from the very first lecture, from the mean and the variance. So the z distribution, we can write it like this. This is the same z distribution that we've always used, right? It's xn minus mu over the square root of n over the variance times the square root of n, right? So but instead of writing these in the denominator, I can just flip them and express them as a product, right? So this is the same z distribution that we've always seen, just rewriting these as a product instead of having them be in the denominator, right? And by definition, right, the mean of this thing will be 0, right? Because we've put it in standard normal format. So you can either think, I mean, we've already proved that the standard normal distribution has a mean of 0, but we can emphasize that to ourselves again, right? We're subtracted off the mu, right? So the mean of this thing is going to be 0, and the variance is going to be 1. Again, almost by definition, we've already proven that the standard normal standard normal distribution has a variance of 0. But we can also think about it. We can also prove it to ourselves, right? Since the variance of xn minus mu is equal to the variance of just xn, because when you add or subtract a constant, the variance doesn't change, right? So the variance of xn, the variance of x average here is just this sigma squared divided by n. And to correct for that, we just multiply by the square root of n times sigma. And because when you multiply the variance by a particular constant, it changes by the square of that constant. So when we multiply those together, these two terms cancel out and you just get 1. So you can think of it that way, or you can just think that we already knew that the variance of a standard normal distribution was going to be 1, right? So we have our z distribution with its mean of 0 and its variance 1. And again, if we know if we use the z distribution for inference, if we know the mean and the variance ahead of time, we can use the z distribution. So we can have this. If we know the standard deviation is 12 ahead of time, in our test, we can use the p norm. But if we are estimating, right? So if I can just type in this sigma here. Right, so I'm just recast my R code for this particular formulation of the z distribution. Nothing else has changed, right? I've just changed the z distribution here so that it follows this form, right? So it's mean minus 100 times the square root of the sample size divided by 12, right? And so it's the same thing. Normally we would think of having the standard error being the denominator, but here I'm just refactoring it so that it's here. Right, so nothing here has changed. If I know this number 12 is ahead of time, I can use the normal distribution corrected for the sample size. If I'm estimating it from the data, I can't use the normal distribution. I have to use the t distribution in order for this to get fixed. So if I just leave it as the normal distribution, the p-values are too small. So why does the t distribution work? So I'm going to rely on, I'm going to need to use smart people to tell us one thing. There's a proof of this here that you can follow on the wiki. But what I'm going to argue is that there's this random variable v, right? So with this random variable v is chi-square distributed with n minus 1 degrees of freedom. This is what we're stating with that proof. So if you have n minus 1 and you have this s squared n, this is your estimate of the variance. Right, so the estimate of the variance is 1 over n minus 1 sum of xi minus xn squared, right? So we recognize this as the estimate of the variance, right? And this is what the variance actually is, right? This is what the variance actually is. Like if you knew the variance ahead of time, this is what the variance actually is. And so we'll state with that proof that the relationship between these two, when you multiply it by the sample size minus 1, or the sample size here can be the same as the chi-squared degrees of freedom, right? So when you multiply that by n minus 1, that this thing is chi-squared distributed with n minus 1 degrees of freedom. So we'll state that without proof. This code actually shows that this is true. Yes, right. So here we're calculating this value, sample size minus 1 times our estimated. So we're calculating our sample size minus 1 times the estimate of the variance, times the estimate of the variance, right? So this variance in R is this, right? We're estimating the data we're estimating the variance from the data, and here we're dividing this by the variance that we knew ahead of time. Okay, so this equation here is, right, n minus 1, sample size minus 1 for sample size of 10, times the variance that we estimate from the data, times the variance that we know is true ahead of time. Right, so this relationship is captured in the histogram in the circles, and that is the same as d chi-square with 9 degrees of freedom. Okay, so this shows that even though we haven't proven that, we've shown that in this case this is absolutely true, that these two things are the same. So what we want to show here, right? So this is the z distribution. This is the thing that we can't use, right? This is the z distribution, the thing that we can't use. What we want to show, is that if we substitute in the variance, right? We don't know the variance ahead of time. We're estimating it. We're estimating the variance from the data, right? So this is the z distribution. It's exactly the same, except we're estimating the variance from the data instead, or the standard deviation from the data, instead of knowing it ahead of time. We want to show is that this is the same as the t distribution. Okay, so we want to show that when we go from this to this, that this is the same as the t distribution. That is to say that this is equivalent to this. So to show that, there's just a little bit of math to show that, right? So the t distribution equals the z square root of v over v, right? But this v, right, is the chi-square distribution at n minus 1, right? So that equals this, right? So we substitute in the v here, right? This equation comes in for the v here, right? And so now, and v itself is also is n minus 1, right? But it's degrees of freedom minus 1. Just that's how we're defining v here, right? So these cancel out, right? These cancel out. And now you have s squared over sigma squared here, right? So the sigma squared pops up here, the square root of sigma squared pops up here, and then you have the square root of s squared here. These cancel out, and so then you end up with xn minus mu times the square root of n divided by s. That's here, right? This is the z distribution with the s here with the standard deviation estimated from the data. So that's the t distribution. So that's why this works, right? So if you let smart people tell you that this is true, and we can demonstrate that this relationship holds for this example in R. So if you let smart people tell you that this is true, you can say that these two are equivalent. That is to say, you go from the z distribution to the t distribution when you go from the standard deviation known ahead of time to the standard deviation estimated from the data. So you guys, there's not going to be a final. There's not going to be a final in this class. That's going to be a closed book final. You guys wouldn't be responsible for this proof, even if there were. But that's just really pretty, right? That tells you why the t distribution works, and emphasizes that what you're doing is changing this variance to a standard deviation. And so just again to demonstrate that this works, right? So here I have my broken code. Here I have my broken code where I was estimating the standard deviation ahead of time, and my normal distribution breaks. So now if I'm estimating the standard deviation ahead of time, all I need to do to fix it is go from p norm to pt. And the reason that works is because then this becomes this. And what this proof shows is that when this becomes this, when you're estimating the standard deviation from the data instead of knowing it from ahead of time, this can be expressed as equivalent to the t distribution, and that's what this proof shows. So that's really nice, and that gives us the t distribution. And in the next lecture, we will finally get to examining how we can use the t distribution to power the t-test.